Hi everyone. So last time we looked at some simple transient circuits with RC combinations. Today we're going to look at RL combinations. So by the end of it, just like the session with capacitors, you should be able to compute voltages and currents in simple switched RL circuits. And you'll see the procedure is exactly the same, except this time we have an inductor instead of a capacitor. And what that means is that when we look at the charging and the discharging, it will be with current instead of voltage. Remember, the voltage across the capacitor cannot change instantaneously. That is the one that takes some time to change. Whereas with the inductor, the current can't change instantaneously. So with the capacitor, we look at how the voltage changes in time, and with the inductor, we look at how the current changes in time. And you'll notice that all these diagrams look very familiar. So what you have here is the switch, which is going to close in here and energize the circuit. The inductor is initially uncharged, and it might sound strange to say uncharged for an inductor, because when we say charged, we think of charge on a plate, but what we mean here is that it is there is no energy in the field of the inductor. So at t is equal to 0, we switch on the switch, and then current we expect will flow, but because we have yet got a little messed up, it is equal to 1 on L integral between 0 and t vt dt, right? Since we have this integral, when t is still 0, we are not going to get a change in the current. If the current tries to change, because you'll have that L di dt, which is going to create a voltage in the opposite direction and prevent it from changing. The full voltage appears across the inductor because there's no current now, and since there's no current through the inductor or the resistor, it means that there's no voltage drop across the resistor. So the full voltage Vs here appears across the inductor. So with the capacitor in the beginning, we had an initial current. Now here we're going to have an initial voltage. And as energy starts building up in the magnetic field, what we're going to have is the rate of change being decreased, which decreases the back EMF across the inductor. That is, the inductor voltage is going to decrease, and when the flux reaches its maximum value, then you're going to have no voltage because there's no rate of change of flux anymore, and we've reached steady state. The inductor in this case behaves like a short circuit, unlike the capacitor, which behaves like an open circuit. So if you remember the capacitor, what happened was charges started moving from one plate to the other and building up the electric field. As the electric field grew, the voltage across the capacitor grew, and that reduced the current coming into the capacitor. In this case, what we have is, as current starts to flow in the inductor, the magnetic field starts to increase. The rate at which it changes decreases, which decreases the back EMF, and that makes it behave like a short circuit. So it's a little more difficult to see than the capacitor. And again, you could go onto YouTube and so on and look for some animations. You have very good ones now, and you'll get a better idea of what happens instead of just looking at the static diagram. Now we're going to go through the same process. We have the voltage across. Once the switch is closed, we are going to write an equation for the voltages in the closed loop. So we start from this side again, and we go up, and we get VL from here to here, plus from here to here VR, plus from here to here, well, it will be minus Vs is equal to 0. And in this case, we know the voltage across the inductor is L di dt, and the voltage across the resistor is simply IR. So we end up with a differential equation again, just like in the case of the capacitor. In the case of the capacitor, we were solving for the voltage across the capacitor. Remember, the voltage changes instantaneously across the inductor, but it doesn't change instantaneously across the capacitor. The current changes does not change instantaneously through the inductor in this case. So that is the one we are solving for. So we write the differential equation, then we go through the same sort of mathematics again, and we come to the same point about solving for our constant. Again, we have to look at what are our boundary conditions. So here we're looking at t is equal to 0. The current through the inductor, just ignore this s, the current through the inductor is 0. So we can find out what the value of that constant is, substitute it into the equation, and eventually we should get this. And you should go through the derivation by hand at least once, just to make sure you follow all the steps, right? And what we will end up with is the current through the inductor is Vs on R 1 minus e to the minus R on Lt. You'll see it's very similar to what was happening with the capacitor. With the capacitor we had Vc, for the capacitor we had Vc was equal to Vs 1 minus e to the minus T on Rc. So the same sort of setup, yes, except here we have T on Rc, here we have minus R on Lt, and we have Vs here, which is the supply voltage. Here we have Vs on R, which is the supply current when the inductor is a short circuit. So this is the final voltage across the capacitor. This is the final current through the inductor when it is in steady state. When the capacitor is in steady state, the voltage across it is Vs. When the inductor gets to steady state, the final current through it will be Vs on R. And again we have here the time constant, which is in this case will be L on R. So when t is L on R, it will make the exponent minus 1. So now we're going to go to discharging, and you'll see we have the same setup here. We initially charge the inductor, and then after a while we discharge it. So we just have the inductor connected to a resistor. So the inductor is connected to the resistor. We write our KVL equation again. We go through our differential equations, and notice, of course, here we write a minus sign, minus L di dt, because the voltage across it for positive should be opposite to the direction of the current. So that's why we just have a minus sign here. So we go through the whole thing again, and what we end up with this time, after we find our constants, right, and again you should go through this at least once by hand. It's the normal way to solve a differential equation, first order differential equation. We will get Vs on R e to the minus R on Lt. This Vs on R again represents the initial current through the inductor. This is, we assumed here, this Vs on R, what it assumes, if you look at here, this will tell the story to you. At t is equal to 0, IL is Vs on R. So this is really IL0, the initial current through the inductor. Yes, when the inductor started from being fully charged, then it will be Vs on R. That is when it reached steady state, so there was Vs on R would be the current that was flowing through it before we switched it into R2. So we have Vs on R e to the minus R on Lt. And again here, we have ignored so far what would happen if the inductor did not have, if the inductor had an initial current through it. And just like in the case of the capacitor, again, we could take that into consideration when we solve for our constant by simply setting it equal to some inductor current. And then when we solve for it, again, we see that we get the superposition of a charging and discharging equation. So if the inductor did have some initial current and then you switched it, it would move toward the new current from the old current. So it would discharge the old current and it would go to the new current. Yes, so you could see it as a superposition of those two, and this is of course the most general form of the equation. So if you can't remember any of them, any of the other equations, this is the one you should remember because it has the both equations built into it. Yes, so now again looking at the time constants, this time when t is equal to ln r, and I think I mentioned this before a little while ago, when t is equal to ln r, we have the same condition that the exponent goes to -1, and we will have 0.3679. So if it is discharging at t is equal to ln r seconds, it will be about 37% charged, and if it was charging, it would be about 63%. Sorry. And again, for 5 time constants, that is what you look at for full charging or full discharging. Good. So I have an example here for you. I'm going to post up the slides. So you could look at this example. You could take it down and solve for these questions. So you have to calculate the time it takes for the inductor to develop 3 amps through it. And again, this is exactly the same procedure as you would have done with the capacitor, except now you're dealing with current and not voltage. And then after that, I would like you to calculate the steady state current through the inductor and the time it takes for this to develop. Good. So that is it for the capacitor and inductor switching. You can see it's very simple. As I said before, we've looked at this only with steady state, with very simple circuits. So either the capacitor or the inductor was connected to basically what is a Thevenin equivalent circuit. And regardless of the circuit you have, you could reduce it into this Thevenin equivalent form. So you may have circuits with not just one resistor, but you might have hundreds of resistors, hundreds of sources in other arrangements. You could always reduce that into its Thevenin equivalent form and put the inductor in it, and you should get the correct answer for the charging and discharging. So you could try that with some of the examples from the textbook and see what you get. And hopefully by now you should be able to compute the voltages and currents in simple switched RL circuits, which means you should be able to do RC, RL, and next time we'll look at RLC circuits. And where the difference here is that whereas RL and RC, they were first order differential equations, RLC circuits, we have to use second order differential equations. So you could go ahead and revise some of that in the meanwhile.